Good evening, everyone, and welcome. We're so glad that you're here. I am Jean-Luc Margot, a professor in the Department of Earth, Planetary, and Space Sciences in the Department of Physics and Astronomy at UCLA. And I'm so grateful that you decided to spend some time to learn about our search for life in the universe and our citizen science collaboration. We have a great panel of SETI enthusiasts and experts to answer your questions this evening, and I would like to introduce them at this time. It's my great pleasure to introduce the moderator for today's conversation, Fritz Demopoulos. Fritz is a California-born entrepreneur, investor, and philanthropist who resides in Hong Kong. He co-founded China's largest travel internet company and China's largest sports internet company, and he's the founding partner of a venture capital firm called Queens Road Capital. Fritz earned an MBA from UCLA, and he has been a big supporter of UCLA, including our efforts at UCLA SETI, for which we're extremely grateful. He's also part of the UCLA Earth, Planetary, and Space Sciences Board of Advisors. Fritz is passionate about exploring science and science fiction, and he cares very much about science education and gender equity in the sciences. I have very much valued all my conversations with Fritz. He is a strategic thinker, he's a big thinker, and he always encourages me to stretch myself and to stretch our goals at UCLA SETI. And I feel incredibly fortunate to benefit from his influence. So Fritz, thank you so much for being here with us this evening. And I'm also delighted to introduce our speaker and panelist, Megan Lee, who is a first-year graduate student at UCLA and a third-generation Bruin. Her grandfather immigrated here in the 60s from Taiwan to complete a PhD in system sciences. Megan got her undergraduate degree in physics and astrophysics at the University of California, San Diego, where she was not only a top undergraduate student in academics and research, but also launched a number of initiatives to improve diversity and inclusion in physics, astronomy, and STEM fields in general. She is the founder and president of Big Sister STEM, which currently serves approximately 50 girls in middle school and high school, and which has paired these young female students with early career women in STEM. Megan is passionate about both SETI and public outreach, which made her an ideal candidate for our group at UCLA SETI and for launching our citizens collaboration, and I am thrilled that she decided to join us. Megan, thank you so much for being here with us this evening. Our event will last approximately 1 hour. I will speak about the search that we're conducting at UCLA for about 20 minutes, after which Megan will speak about the citizen science collaboration for 10 minutes. And we want to leave 30 minutes to address your questions. So please use the audience Q&A button at the bottom of your screen to ask any question you may have, and we will try to get to as many questions as we can. Imagine what we could learn if we established contact with an advanced civilization. Today, I want to talk about the search for life in the universe, which is part of a discipline known as astrobiology. And the big questions in astrobiology are as follows. How did it all happen? How did we end up with this beautiful planet that can sustain life? And is there life elsewhere? And is there possibly intelligent life elsewhere? And could we communicate with other civilizations? This search is tied to some of the most important questions in science. And in particular, one of the big questions in science is what is life? And at the moment, we have a real difficulty in forming a general theory of living systems because we have only one example of life on Earth. All life on Earth is connected to the last universal ancestor. And this common origin really blinds us to the possibilities of life elsewhere, and it prevents us from fully understanding what life is. So the discovery of another form of life, anywhere, of any form, will be a tremendous advance for the sciences. For that reason, federal agencies, science agencies, are investing billions of dollars in the search for biosignatures. A biosignature is any evidence of biological activity. And we can do the search for biosignatures in a couple of ways. We can send robots to the surfaces of a handful of planets and satellites in the solar system. And these robots are going to scratch and sniff the surface and look for fossils or evidence of metabolism. And another way is to send a large telescope in space and observe nearby exoplanets and look for signatures in the atmospheres of these exoplanets of potential biological activity. There's another way to search for life elsewhere, and that is the search for technosignatures, and that's what we'll be focusing on today. A technosignature is any evidence for technological activity. Essentially, we're searching for other engineers out there in the galaxy. Now, why do we think that life might exist elsewhere? Well, first of all, we've observed that the building blocks of life, such as the amino acids, are found everywhere in space. They're found in the interstellar medium. They're found in meteorites that fall on Earth. And so the ingredients for life seem to be prevalent. And we also know, thanks to the Kepler mission, that there's an abundance of planets out there. Kepler was a mission that observed a part of the sky that was about 10 degrees by 10 degrees. That's about the size of your fist at arm's length. And it observed this region of the sky near the constellation Cygnus to detect planets around other stars. And the way the Kepler telescope works is illustrated here. If you were fortunate enough to see the transit of Venus in 2012, it illustrates how the Kepler telescope works. When a planet passes in front of a star, the total amount of light from that star decreases by a tiny amount, but that amount is measurable. And Kepler observed these repeated decreases in the amount of stars from more than 100,000 stars and inferred the existence of planets around those stars. Kepler really revolutionized the field of astronomy. I like it to call it the second Copernican revolution or the Kepler revolution. The chart on the left illustrates what we knew about planets before Kepler. And the chart on the right illustrates what we know now after Kepler. It's been an enormous change in our understanding and knowledge of the number of planets. So Kepler quantified the number of planets around other stars, and it also showed that the most abundant type of planets are planets like Earth. It showed that essentially every star in the galaxy has a planet on average. Now, what does that mean? There are 100 billions of stars in the galaxy. So that means that if you wanted to count the number of planets in the galaxy, and you could count them maybe at a rate of 1 per second, let's say, it would take you about 3,000 years to complete the inventory of planets in the galaxy. And that is just in our galaxy alone. And there are hundreds of billions of galaxies out there. So the number of planets in the observable universe is astounding. To get a sense for that number, you have to picture yourself going to a beach and counting the grains of dry sand on that beach. I'm going to give you a second to imagine yourself doing that. But then you need to imagine yourself doing that on all the beaches on Earth, because the number of planets in the observable universe is roughly comparable to the number of grains of dry sand on all the beaches on Earth. So we have a profusion of planets out there. And one question is, what fraction of those planets is habitable? We know the answer for the solar system. It's at least 1 in 8. And Kepler allowed us to quantify this number for other planetary systems. And Kepler has shown that, in fact, there's something like tens of billions of potentially habitable planets in the Milky Way galaxy. So we live at a very interesting moment in the history of science, where in the last 10 years, we figured out about the number of planets and the number of habitable planets in our galaxy. And this is illustrated in an equation, a famous equation called the Drake equation, that quantifies how many communicative civilizations there might be in the galaxy. So n is the number of communicative civilizations. It depends on the rate of star formation in the galaxy and the fraction of stars that have planets, and the number of Earth-like planets in those systems, and then the fraction where life might originate, intelligent life might originate, and communicative life might originate. For the first time in the history of science, we've now quantified these numbers, and we know that these numbers are large. So even if the probability of life arising and developing into an intelligent species is low, we're multiplying those low numbers by a very, very large number. And so it is not unreasonable to think that life is abundant out there, and that even possibly intelligent life is abundant out there. So we live in this phenomenal universe where the laws of physics and chemistry have allowed for the formation of stars and planets and for the building blocks of life. And we're on a quest to try to find out if we're alone in this universe or not. So again, the primary search techniques focus on the search for biosignatures, and we're investing tens of billions of dollars in doing this. And I want to talk about the search for technosignatures, which I think has 4 compelling advantages compared to the search for biosignatures. And the first one is cost. I just mentioned the cost of these biosignature missions. I fully support the biosignature searches, but they're expensive. And I support them because the question is so important, right? We really want to find another evidence for life elsewhere. But for a fraction of that cost, we can have a very, very robust search for technosignatures. So we're talking maybe $10 million a year instead of $10 billion. The second advantage that I see has to do with search volume. When we're looking for biosignatures, we're looking at a tiny bubble around the sun. We're looking at a handful of places in the solar system, or dozens of exoplanets very near the sun. And that's a tiny, tiny fraction of the Milky Way galaxy. Whereas with technosignatures, we really open up that search volume to the entire volume of the galaxy, a volume that is about 1 million times larger than what we sample for biosignatures. A third advantage has to do with the certainty of interpretation. Many biosignature searches have false positives. In other words, they may detect oxygen in the atmosphere of an exoplanet, but that does not necessarily mean that life produced that oxygen. There are geological processes that can produce similar signatures. So there's a framework that's evolving that is more of a probability assessment as to whether there's life on a planet if such a biosignature is detected. In contrast, the signals that we're looking for in some technosignature searches have no false positives. In other words, there is no way for nature to generate them. And therefore, if we can identify such signals, we will have pretty compelling evidence that there is another civilization out there. It won't be a probabilistic assessment. It will be a very compelling piece of evidence. And then the fourth and final advantage that I see is the potential information content. If we detect a signal, it may have information encoded in it. And the potential for advances in human knowledge are extraordinary. And to understand that, I like to describe the cosmic calendar, which was popularized by Carl Sagan. And this is a calendar where you put the entire history of the universe on a calendar, where the Big Bang starts at January 1st, and this evening, we're at midnight on December 31st. Now, on this calendar, the Earth forms in early September, and all our technology, our ability to communicate with other civilization, all of that happens in the last 1 second on December 31st on that 1-year calendar. And so the question that we have to ask ourselves is, if we get a signal from another civilization, what is the probability that they developed their technology in that same 1 second slice of this 1-year calendar, right? It's almost zero. It's almost an impossibility statistically. And it has nothing to do with the time that it takes for the signal to get to Earth. It has to do with just the probability of arising as a civilization over that 14 billion period history of the universe. So it's almost certain that another civilization would have evolved at a different time on the calendar, which means that they are more advanced than we are by thousands of years or millions of years. And so again, we have the potential to establish contact with a civilization that is far more advanced than we are. Imagine what we could learn. Now, how can we do the search? At UCLA SETI, we've decided to search in the radio part of the electromagnetic spectrum for a couple of reasons. First of all, radio waves are very easy to generate. They're very cheap to generate. And radio waves propagate at the speed of light in a very straightforward manner. The universe is pretty transparent to radio waves, so they propagate long distances without attenuation. So they're really, really good if you're trying to communicate with someone. So we're looking at a part of the spectrum here near the 1 gigahertz frequency range, where the properties of the atmosphere are also very good, very transparent to these radio waves, and where there's a pretty fundamental line that every radio astronomer of every civilization will know. It's called the hydrogen line, and where hydrogen is the most important element in the universe, and it has this very important transition that can generate a specific radio wave at a specific wavelength. So that's the part of the spectrum that we're looking at. We're using the largest fully steerable telescope on the planet, the Green Bank telescope in West Virginia. It's about 300 feet in diameter. And with that telescope, we're able to detect the equivalent of an Arecibo radar system, right? So this is a 1 megawatt transmitter that our fairly primitive civilization was able to build. And we can detect even that telescope hundreds of light years away. Now, if civilizations are more advanced than we are, they can undoubtedly generate more power than the Arecibo telescope could, and therefore it opens up the detection space to pretty much the entire galaxy or even beyond, depending on the transmitter power. How much of the search space have we covered? And this is not very easy to quantify. There are a couple of metrics out there. They're not perfect, but a rough analogy is that we may have sampled about a bathtub's worth out of the Earth's oceans, right? So there's a vast search volume out there, and we've not sampled a very big fraction of it. So there's a lot of potential for additional searching and discovery. Now, here are some numbers about the UCLA search. Since 2016, we've been using the Green Bank telescope to observe a number of planetary systems. We've observed about 100 different stars so far, but because the beam of the telescope has a certain width, invariably when we point at one star, we are capturing hundreds of stars and planetary systems, and we're sensitive to signals emitted from any of those. And so in reality, we've sampled something like 41,000 stars. We've detected about 64 million narrowband signals. By narrowband, I mean they don't span a wide range of frequencies. The energy is very concentrated in a small range of frequencies. And we know that nature doesn't do that. And that's why we're looking for these kinds of signals, because they would be pretty compelling. And so we have a really high efficiency in our search. If you're trying to quantify how many signals you detected per unit bandwidth, per unit hour of telescope time, we're doing very, very well on that metric compared to some of the other searches out there. We've also incorporated this search as part of an annual class, a full-length SETI course, which is really fun to teach. This is a project-based, learn by doing course in which students design an observing program for the Green Bank telescope, observe with the Green Bank telescope, download terabytes of data to UCLA, and then write algorithms in small teams to improve our data processing pipeline, to analyze the data. They present their results in class, and then we write papers in the peer-reviewed literature with all of these students who have contributed very meaningfully to our search as co-authors on these publications. So it's a really fun course. We've taught it to about 120 undergraduate students so far and about a dozen graduate students. So I've just mentioned one of the most important questions in science: are we alone in the universe? And what are we doing about it, right? We have this amazing search technique, the search for technosignatures. And remarkably, federal agencies have invested very little in the search for technosignatures. We're talking about a few $1 million over the past 30 years. That is an incredibly small amount of money, considering the importance of the science and our capabilities. So there are ways that you can contribute. You can contribute by actively contributing to the search. We'll explain to you how to do that now. And if you're in a position to do so, you can help by enabling the search at UCLA. So join us at arewealone.earth, where you can contribute actively to the search. Or if you're in a position to do so, there's opportunities for giving at every level, and we would love to have your support. If you go to seti.ucla.edu, you'll see how you can give. Or there are people on this call who are part of our development team who can assist as well. All right, I want to pass the baton to Megan, who will tell us about our citizen science collaboration that just launched a couple of days ago. Go ahead, Megan.
Yes, thank you. Hi, good evening, everybody. My name is Megan Grace Lee, and as mentioned, I am the grad student working with Jean-Luc on this project. Thank you for giving me the nicest introduction anybody has ever given me earlier. And I am really excited to share with everybody more about our platform, specifically our science goals and how to get started. So this is Are We Alone in the Universe, a citizen science collaboration. So to quickly recap, UCLA SETI searches for narrowband radio signals, and we have some examples of these here on the right. We collect millions of these per year, and what's really cool, as mentioned, is that these are collected with the students in the UCLA SETI course taught in the spring. So I'm really excited for that class to happen again next quarter. I'll definitely be in it. So there is so much good news about our search. Not only do we find millions and millions of these signals, 99.5% of them are automatically understood by our current computer algorithms. And mostly these turn out to be terrestrially radiated radio signals, meaning they're not from ET, but they are from Earth. But that leaves 0.5% of the most interesting signals. And that does end up being several 100,000 signals that need to be searched through with the human. And that's where you come in. So please enter Are We Alone in the Universe, which is a platform where you and I can look through just the best of the best signals, or the top 0.5%. The science goal of Are We Alone in the Universe is to form a labeled training set for future machine learning algorithms that Professor Margot and I will be developing once the project is completed. So if you're not super familiar with the words in blue, no worries, I'll be covering that next. First, to learn about machine learning, here is a quick video using watermelons.
You used to go to the store, pick up a watermelon, maybe your family told you push on the end to see if it's soft and that means it's a good watermelon, or if it smells a certain way. That's how you tell if it's a good watermelon. Well, with machine learning, you don't do any of that. You basically try to determine all of the attributes about this watermelon that you can, and you take those attributes and you feed them into a baby machine model that knows nothing. How fat the stripes are, how thin they are. And you feed all these attributes into that model, you go home, you eat the watermelon. You come back in the next day and you tell that model, that was a good watermelon. And it remembers all of those attributes and the fact that it was good. And you're gonna do that every day for the next 10 years. After 10 years, that model is gonna be able to tell you, based on attributes that you give it, if the watermelon you've picked up is good or bad. And you may not know why that model is telling you it's good or bad. But you can trust that it has done enough analysis and it can tell you a percentage, a surety of whether it's good or bad, that when you pick up a watermelon, give it the attributes, if it says it's good, you can take it home and it will be good.
Cool. So now in a nutshell, or in a watermelon rind, we know that machine learning is when your computer learns whether or not something is good or bad, or fulfills a certain trait based on looking at those things over and over again and classifying them into different categories. So the classifications of all of these watermelons into different categories form a labeled training set. And you can do this based on a number of characteristics about the watermelons, such as shape, size, color. But what if you wanted to do some stripe analysis? So I have some watermelons here on the left, and if I wanted to make a labeled training set out of these watermelons using stripes, maybe I could call these something like plain, narrow, wide, and diffuse. And as mentioned, we want to know which watermelons are going to taste good without having to crack them open. So let's say eventually our machine learns that the wide watermelons are the best. Eventually, it will just start feeding us only wide striped watermelons. So how exactly does this connect to looking for ET? Well, these watermelon stripes actually look a lot like the radio signals that you'll be sorting on Are We Alone in the Universe? So on the left, I have some examples of the radio signals that are currently available on our platform. And just like with the watermelons, let's say I wanted to train our computer. So I would call these things like wavy, bright bunch, and striped. And one of the best parts of Are We Alone in the Universe is we're not exactly sure what we are looking for yet. We're just going to spend a lot of time classifying all these different signals into our cool categories. And hopefully from there, we can make inferences into how to better look for ET. So here's a quick playthrough of Are We Alone in the Universe? So after you go to our URL, arewealone.earth, you can hit classify or get started, and they will immediately hand you a signal to begin classifying. From there, you will answer a series of short questions, such as whether or not the signal is more vertically aligned or more horizontally aligned. And eventually, you will select the image that most closely matches the signal that you've been handed. However, it gets a little tricky. Not all of them are as straightforward as the one that I just showed. So we do have a tutorial to briefly explain to you some best practices of sorting these signals. So for example, some of the signals are going to have huge horizontal dark bands across them. Do your best to ignore them. They're just that the signal got a little bit quieter for a few seconds. And there are a few other caveats that we're actually in active discussion about right now because we've been on Zooniverse for quite a few days. So other than our tutorial, there's also the field guide. And my favorite tab of the field guide is this last one, classification task, which shows larger images of the 20 available classes on our platform. And one of the best parts about Zooniverse is that if you ever get stuck on a signal, you can automatically post that signal to the talk board, where a member of the science team, like myself, Professor Margot, will take a closer look at the one that you're working on and answer your question. So here's a closer look at the 20 classes of available signals on the platform. So from answering whether or not the signal is horizontal or vertical, you will unlock some set of 4 images that you'll want to match your signal to. However, we do recognize that these 20 different examples do not cover all of the signals that are currently in the database. So there's actually 20 plus 1 available classes where the plus 1 is the other category. And there is already a lot of active discourse on signals that need to be classified in other. And these are super interesting because we don't know a whole lot about them yet. So I know what you're all wondering. How do I get started? I want to start playing right now. Well, first, you'll want to visit our URL at arewealone.earth. From there, you'll need to create a Zooniverse account. And Zooniverse is a platform that hosts a plethora of different citizen science initiatives. So that's definitely a great account for everybody to have. And finally, you should be sharing us with everybody you know. We recommend Are We Alone in the Universe to everybody 10 plus, which means that we're a great candidate for activities in classrooms, school clubs, and family reunions. So Are We Alone in the Universe launched on Valentine's Day. So a lot of us had an extraterrestrial as our Valentine, and we've already made so much progress. So at our pre-launch stage, we had 256 beta testers, and they completed 5,000 classifications to help us test out the product. And by today, we have over 1,800 volunteers and over 75,000 classifications. And that is absolutely tremendous. We are so grateful for everybody who has volunteered and very excited to see where this project will be going. So finally, I'd like to thank both the Planetary Society and the NASA Citizen Science Seed Foundation for funding our project. We are so grateful that you are allowing us to pursue our passions of both SETI and public outreach. And we'd also like to thank all of the beta testers, volunteers, and the Zooniverse team for all of the work that they've already put into Are We Alone in the Universe? And finally, all of you for listening. Thank you.
All right. Thank you, Megan. That was great. Fritz, would you like to start with a question?
Yeah, Jean-Luc and Megan, thank you very much for doing this. I think in the history of science, the real winners are those who take the path less traveled. And I think that's what you've been doing your entire career. And Megan, kudos to you. I know you're starting your career and you're taking this path, so we appreciate that. But my question, it's just a basic question. Where is everybody?
That's a great question. Sometimes known as the Fermi paradox, although some people debate whether it's an actual paradox or not. So it goes back to apparently a lunch conversation that the physicist Enrico Fermi had with some colleagues. And the argument goes as follows, right? So if we've had 14 billion years in this universe, if civilizations exist, they could possibly build interstellar machines, spacecraft that could cross the Milky Way galaxy in a fraction of the time of the lifetime of the universe, right? And that's the argument. If they exist, and if they have the capabilities that we tend to assume they have, why wouldn't see evidence of other civilizations around us? And it's been extended a little bit to say, well, why aren't we detecting their signals either, right? So in terms of the interstellar travel, I'm not sure that it's so easy to cross the galaxy, right? So even if you have the best technology available, you're still subject to the laws of physics. And the laws of physics are a very serious impediment to you traveling across the galaxy, right? You cannot travel faster than the speed of light. The galaxy is 100,000 light years across. So even if you could travel at the speed of light, but you can't, it would take about 100,000 years to cross the galaxy. And whenever you approach any kind of substantial velocity, any grain in your path is going to, be a little bomb to your spacecraft, essentially, because the velocity is so high that even a small particle would create a huge obstacle and a very large explosion. So interstellar travel may be much harder than we expect. There may be other sociological reasons for why they're not interested in colonizing other planets. Maybe they're just observing from a distance. We don't really know. So I'm not particularly discouraged by the fact that we haven't seen any evidence so far. And I think that we haven't searched a huge part of the search volume, and it behooves us to do more. Megan, do you want to add anything?
No, I think you covered all of it.
Jean-Luc, you said, in fact, your opening sentence was, imagine what we can learn if we discover or come in contact with an extraterrestrial civilization. You know, what 2 or 3 questions would you ask? And maybe Megan can also answer that.
Well, and this relates to a question that's been posted in the chat. When I say establish contact, what I really mean is listen to the transmitted signal, because again, the distances are considerable, right? So if you're detecting a signal from a civilization that's, let's say, 10,000 light years away, it took 10,000 years for the signal to get here, right? So I'm not anticipating any kind of two-way communication. I'm really interested in listening, detecting that signal, and then figuring out whatever it is that's encoded in the signal.
Yeah, exactly. As much as I would love to be texting buddies with an extraterrestrial, I don't think distance is going to allow that to happen. This long distance relationship is sadly not going to work. But I think the discovery of anybody else in our universe at all would just be such a profound step for humanity. And we would all just learn a lot from not being the center of our own universe anymore.
Daniel Gutierrez in the audience, he had some questions about the Drake equation. He was wondering about if we can dive into the F, but maybe broadly speaking, when you look at the Drake equation, we've learned a lot, as you've highlighted. What are parts of the equation that you think are still up in the air that we need to, are too speculative?
Right, so those F values, right, the fraction of habitable planets where life emerges, the fraction of those that turn into intelligent life, and the fraction of those that decide to communicate, all of those are completely uncertain, right? We really don't know. And so when we're doing the search, at some level, we're making a hypothesis. We're making the hypothesis that those values are non-zero and that there are some civilizations out there. And we can test the hypothesis by trying to detect signals, right? We'll test the hypothesis that way. One of the things that has evolved in terms of thinking about the Drake equation is that that last term, the L term, is, stands for lifetime, the average lifetime of a civilization. And I think the current thinking is that if a single civilization figures out how to survive technological adolescence and establish a long-lasting civilization, then the Drake equation becomes sort of not particularly useful, because you have that one civilization that is, in existence for millions or billions of years, and all it takes is one civilization, right? So the value of L becomes almost insignificant. And I should say the value of L is also completely speculative at this point.
Jean-Luc or Megan, there's another very interesting question, and I think it relates a little bit to the James Webb Space Telescope as well. Michael Carlin, he was asking about, you mentioned a lot about, hey, look, there's a lot of potentially habitable planets out there. And his question was, do we think about just the distance from a star, or do we need to also think about atmosphere? And with these new instruments, such as James Webb, we're able to get a better sense of these atmospheres. How should we think about that?
Right, so the traditional definition of the habitable zone is that region of space around the star, the range of distances from a star where liquid water could exist on the surface of a planet. And indeed, that pretty much requires an atmosphere, because otherwise the water would just sublimate. So just because a planet is in the habitable zone doesn't mean that it necessarily has an atmosphere, right? So we can think of a planet like Mercury that is so small, it cannot hold on to an atmosphere. All its atmosphere is gone. So that's why I say potentially habitable, right? We don't know exactly how many of those are actually habitable, but it's such a large number. And the presence of an atmosphere around a planet like Earth is such a natural outcome of the process of planet formation that we understand that a lot of these planets are going to have atmospheres. And if they're the right distance from the star, then you can have liquid water. And liquid water is really that magic sauce that makes the chemistry of life possible. And that's why we tend to look for environments that have liquid water.
Well, what do you think about, James Webb is a fantastic instrument, and there's other instruments in the queue, right? And so all of us taxpayers, it's kind of great, I guess, we're funding all this sort of stuff, right? Also including the cost overruns. And I'm just kind of wondering, what instruments in the queue, that are in the pipeline are you super excited about that are going to help us?
Right. So the astronomy community has what's known as a decadal survey. Every 10 years or so, the astronomy community gets together to come up with the next big priorities, the big funding priorities. And then they write this report. It's a huge effort. People get together, write white papers, and then there's a committee that puts out a report. And with that report, we go to the funding agencies, right? NASA, the National Science Foundation, and we say, hey, as a community, we think these are the most important priorities. And in the latest decadal survey, there was a big push for telescopes even more capable than James Webb Space Telescope to try to detect biosignatures. James Webb may be able to tell us if there's oxygen around other planets, but it won't be able to give us an unambiguous answer about whether there's life on other planets. And so you really need the next generation of instruments to do that with better sensitivity, better resolution. And those instruments, unfortunately, are very expensive. And because we have a bunch of instruments in the pipeline, their anticipated launch date is not until the mid-40s. So that's a long wait to try to find life elsewhere. And again, with technosignatures, we can do the search right now. And we can expand that search from primitive life to complex life, and from the solar neighborhood to the entire galaxy.
Hey, Megan, Paul Thompson asked a question. He kind of sounds like a CEO, because only a CEO would ask this question, which is, how do you know that this initiative is going to work out for us? How do you define success with Zooniverse and getting people to participate? Is it 10,000 participants? Is it 1,000? How do you think about that?
Well, Paul, that is a great question. You do definitely sound like a CEO. There are so many different directions in which Are We Alone in the Universe can be successful. There's great science findings, such as we could find a technosignature. There could be one in the data set right now that we haven't run into. We could learn a lot more about how terrestrially generated radio signals are affecting our detections of technosignatures, which is sort of our main goal right now. But there's also, like you mentioned, the community aspect of Are We Alone in the Universe? We have already reached thousands of volunteers. And I think that in itself is already a huge success. And as Jean-Luc mentioned, I do run a volunteer organization for young women. And I always tell my volunteers, if we could just make one girl's day brighter, make her a little bit more excited about science so that she spends just another day wanting to be a scientist, that is already enough for me. That's a huge success. So I think getting the community excited about science and excited about SETI is my personal definition of success.
Agreed.
Well, maybe to build on that, Megan, we have over 100 people on the call today, and some of them have kids. And what's your advice to them to get involved in this? What should they be studying? Should they drive down to Westwood and meet you in person? What's your advice?
Well, I would love that. I I don't always have time to meet every single one of your children, but if I could, I definitely would. And I would spend hours and hours teaching them about all the wonderful things in astronomy. I think definitely exploring your universe. Our wonderful chair, Gabrielino, just mentioned that UCLA every year hosts a huge science fair called Exploring Your Universe. It's in early November every year. So we hosted it last year on November 6th. Jean-Luc actually came and brought his son, Max, and I got to meet Jean-Luc's son. And we had over 12,000 attendees with so many families becoming more and more excited about science. I think the best thing that parents can do to get their children excited about science is to get involved themselves and realize that it's not just for people who are career scientists like myself and Jean-Luc, but it's for everybody, and everybody can get involved with Are We Alone in the Universe?
Hey, Jean-Luc, if we find a signal, say, or you find some great evidence, I'm curious, who are you going to tell? How does that work?
Well, first of all, we'll have several stages of confirmation to make sure that it really is what we think it is, right? So we've had several instances where a signal looked interesting at first glance, and then we spend a few minutes and realize, oh, no, that's not it. So we have several tests that we can do to confirm a signal. If we run out of tests internally, then we'll immediately share our data with other scientists and groups so that they can run their own analysis on the same raw data. So we preserve all the raw data. Make sure there's nothing, there's no bug in our algorithms or something like that. And then we would go back to telescopes. We would go back to Green Bank, and we would go bac to other telescopes and re-observe that same region of the sky, which is similar to what you do in science, right? You want to confirm a result. Reproducibility is sort of at the core of science. So we would go back to different telescopes, run it through different software, run it with different teams. And then only then, if it really is, if it survives all of these tests, then there would be some kind of announcement.
Have you, or how many times have you been in a situation where your internal tests continued to be, I guess, positive, and then you started sharing it outside the UCLA community? Has that happened?
That has not happened yet. No, unfortunately.
I see. And hey, I know we talked about this before. Should we respond? Should we zap back a message, that says, "Hey, look, we just elected President Biden again," or something like that?
This is a topic known as active SETI, right? The fact of intentionally sending a transmission either to be detected or in response to a potential detection of a signal. We haven't consulted broadly or globally on this issue. And so my personal opinion is that we should not do that. And first of all, because we haven't consulted, but second of all, because we don't have that much to offer in a sense, right? We're very, very young civilization. I imagine that if there are other civilizations, they're all going to be far more advanced than we are, again, based on that same probabilistic assessment. And therefore, I think our resources are better spent doing the listening right now and trying to learn, as opposed to trying to broadcast about our elections or anything like that.
Or maybe some latest K-pop band, I guess, right? At least that's what my daughters would love to communicate.
I would be in favor of that, but we shouldn't transmit anything.
I get, you're right, because we should be careful what we transmit. I suppose it's a reflection of our values, and so I don't know what K-pop would mean. I mean, maybe it's a good thing. Jean-Luc, Tom Gingell, Frederick, and John Myers all asked similar questions, which relate to, do we partner with Breakthrough Listen, for example, the SETI Institute, or what other universities do we like working with on this? Or do we like to, like in the true spirit of entrepreneurship, we don't want to work with anyone except ourselves. How do we think about that? And maybe shed some light on that.
Sure. Yeah. So we have very good friends at Berkeley who've been doing SETI for many years. We've exchanged some data. there's actually a lot of value in having independent data processing pipeline, right? So we keep each other honest at a certain level. So we have a different way of writing the algorithms, and look, we find 200 times as many signals per unit bandwidth, per unit time of telescope time, right? And so that then gets communicated to them either verbally or through a peer-reviewed publication, and they can then go to their algorithm and say, okay, well, how can we improve this? And vice versa, right? So they're doing things that we haven't been doing or haven't thought about. And so the whole field sort of grows by having this friendly competition between the different teams. So we don't have formal connections with the SETI Institute or with the Breakthrough Listen initiative, but we know the people in the field. It's a small field, and they're great people to talk to, and we do that at conferences.
Yeah, Jean-Luc and Megan, artificial intelligence, and it's kind of funny. Everyone thought Silicon Valley was dead this year, and all of a sudden they're like, "Oh no, look, no, this is we are actually adding value. Look, AI. Look at this Chat GPT thing." How is what's the role of AI and advanced systems and techniques in our search for extraterrestrial intelligence?
Megan, you want to take it?
Sure. Well, as I mentioned, there are several 100,000 signals to look through, and Jean-Luc and I could do this manually, but it'll take us, a few hours, and there's some element of like humans are looking at this and we're imperfect. So the role of AI here is to first learn from the humans, and that's what Are We Alone in the Universe is doing. We're simply training the AI right now using humans. So right now we have 15 people checking each signal before it joins the label training set. And then once the AI learns from that, the AI will be faster and probably better than us at combing through these signals.
Right. And I'm going to follow up by addressing one of the questions in the Q&A about the watermelon example and how it's a little bit different from what we're doing. So we're training an AI tool to recognize the radio frequency interference, right? And so this AI tool will essentially speed up our search because it will immediately recognize, oh, that's a GPS satellite. Oh, that's an airport radar system, right? And it will recognize those and essentially throw them out of consideration. And that's going to help us focusing on the signals that are not immediately recognizable as RFI. I'm sorry, I used jargon there, as radio frequency interference.
It's okay. I mean, most scientists do that, right? Jean-Luc, I remember once you had sent me an email, maybe a year ago. You're at a conference and we talked a little bit about some of the work you're doing, great work. And you said it was interesting, for the first time, no one was giggling.
Right.
And what's changed? Give us a sense, as it seems like we're entering a new era. What's changed?
Yeah, I think that's a really important change in the community. There used to be this giggle factor, right? Astronomers laughing at people looking for technosignatures. And there's a palpable difference. So at the latest meeting of the American Astronomical Society, Megan and I both presented at that meeting, and there was an entire session called Technosignatures. And in addition to that, there was another session called Astrobiology, where there were a number of talks about the search for technosignatures. That is a change. That is new, and it's exciting because it really means that if there's support from the American Astronomical Society, there's potential, at least, for additional funding from some of the federal agencies. So the field has really been starved for decades by lack of funding from NASA. And we're hoping that the increased acceptance of the search for technosignatures is going to lead to additional funding.
Can people in this audience, should they be sending letters, or I guess emails, to their congressmen and women and tell them this is important, or is there? So what do you think about that?
Yeah, actually, there was in one of the recent budgets from Congress, there was a not so much a directive, but a recommendation that if the NASA administrator, had some technosignature programs, that they ought to fund them. So there's not a mandate for NASA to fund technosignatures yet, but it's getting into the language of the budgets these days. So yes, of course, you can always write to your Congress people and share your enthusiasm and the importance of SETI.
Really, all it is one fighter jet is what we're asking for, right? In terms of money, right? How much is that, right?
Right. That would go a long way to build a very robust search.
And one thing, I know the audience members, can you share with us a little bit more? You had a chart on some of the needs we had, right? And some funding and obviously we love people's time, talent, and their treasure. And can you just give us a sense, what's super important right now?
Right. So, we've observed 40,000 stars. We would like to do 1 million stars, right? And that would take some amount of telescope time, some computer equipment, and some people to actually do the analysis. We were successful in getting one grant from NASA, a 3-year grant, and that's what allowed me to hire Megan. But the grant only funds a graduate student. It doesn't fund telescope time. It doesn't fund equipment, right? So the only way we've been able to do this search really is through the generosity of people like you and others who've contributed to the initiative. That's how we purchase the equipment. That's how we purchase telescope time. And, with our partners at the Planetary Society who've sponsored this initiative, and with a small additional grant from NASA, we've been able to establish this citizen science collaboration. We have a small team of students, right? We want to pay them so they can feed themselves. So yeah, any contributions will really help to further our search.
Yeah, so I love that goal. There's 1 million stars. We want to look at them. We want to analyze them. That's a goal. Do you think we can get that done in a few years with the funding?
With the right funding, we can do this in 3 to 5 years. Yeah.
I like it. 3 to 5 years. And by that time, Megan will be I guess you'll have your PhD by then. Is that right?
That's right. She will be one of the 12 who got a PhD in this field.
And one of very few women.
Correct.
Well, which is, again, it's super important, diversity across multiple dimensions. This is very important. I would like to thank, the audience, including a number of people. We couldn't answer their questions, like Russ Caballero, Manuel Cabo, Leo Marcus, and a bunch of others. I'd like to thank all of you for asking questions. We couldn't get to all of you, but I know that Jean-Luc would and Megan would be very happy to kind of respond to your emails. We'd love for many of you to join us in this adventure. If you think about it, there are not many, I think, amazing opportunities in this world. Frankly, sure, you can go to a K-pop band concert, I guess. I suppose some people might define that as amazing, but frankly, we're at the forefront of something that I think could be, pretty remarkable. And, I'd like to thank Jean-Luc, Megan, of course, Carolina, who heads the department, and everyone else at UCLA for really, trying to make this happen. And I'd encourage everyone who's on the call today, if you wanted, and I've stepped up to join this adventure, and I feel like I get a front row seat. So Jean-Luc has promised me he would call me before he calls President Biden. And so, and maybe you too. So, and so I'd like to thank everyone.
Thank you, Fritz. Yeah, it's time to conclude our event. And thank you for mentioning the questions that are unanswered. So we're going to ask our friendly team to try to save those questions. We'll try to get to them. We do have a newsletter, so we can maybe address some of these questions in our newsletter. Go to seti.ucla.edu and you can subscribe there, or you can join us on Zooniverse at arewealone.earth. So I would like to thank everyone for attending this evening, for spending some of your time to learn about our initiative, and for your amazing questions. They were great. I'd like to thank the UCLA team who helped organize this event, and our amazing speaker and moderator, Megan and Fritz. I hope to see many of you on the Zooniverse platform, and stay tuned. We're going to have an event in the future, perhaps in the fall, to tell you more about the results of the collaboration. Thank you, everyone.